In this video, we're looking at some notes on factoring sum and difference of cubes. Remember, sums means addition, difference means subtraction, and cubed means something to the third power. So that's what we're looking at. If we're factoring sum and difference for cubes, we have two kinds. The sum of cubed means we have something cubed plus something else cubed, or a cubed plus b cubed. If we have a difference of cubes, then that's a cubed minus b cubed, because instead of being added, the two cubes are subtracted. These are two formulas that we have up here of how we can factor. This is something that we should really memorize, these two formulas up here. Let's look at what can help us make this a little easier to memorize. If we start out with a cubed plus b cubed, our first factor is a plus b. So we lose the cubes, and the sign in the middle is the same sign as we had in the original problem. Then we have a second factor. In the second factor, the first and the last terms are the squareds, a squared and b squared. The middle term is the product a times b, and then the signs, the first sign is the opposite of the original problem, and the last sign is always positive because it's a squared term. The same process works if we have a cubed minus b cubed. The first factor is a minus b. That's the same sign that I had in the original problem. In the second factor, again, we're going to follow this pattern where the first term is the square and the last term is the square. So those a squared and b squared, and the middle term is the product. That's the same pattern as we had above. Now in this one, if we started with a minus in our original problem, then our next sign is the opposite, so it would be positive. And the last term is again always positive because it's a squared. So where did this formula come from? Well, we'll do some division later on and see where it comes from. But let's just prove right now that if I did this backwards, so rather than factor, if I started out and found the product of the two terms, that it would give me back what I started with. If I took a plus b and I multiplied it by a squared c plus b squared, then the product of those things should turn into, hopefully, cubed plus cubed. So I'm going to use my area model multiplication here, and a times a squared is a cubed. A squared times b is plus a squared b. Then I have a times ab with a negative is minus a squared b. And then I have a minus ab squared. Up here I have a plus ab squared. And down here I have a plus b cubed. So when I go to put all these things together, what I notice is I have a plus and a minus a squared b. I have a plus and a minus ab squared, and those two terms drop out. So the only thing I have left is the a cubed and the plus b. So everything in the middle dropped out, and this was my product. Therefore, working backwards, these two on the outside are my factors, and that's where my formula comes from. Same thing would have worked if I did a cubed minus b cubed. Okay, so this is our general pattern, but let's see if we can go through and do some example problems of how we're going to use this to do our factoring. Let me leave that up in the picture. Okay, so starting out, I have x cubed plus 27. I have to be sure that both the first term and the second term are perfect cubes. X cubed is pretty clearly a perfect cubed because it already has the cube in it. 27 is 3 cubed. I don't need to write it as 3 cubed, but it'll definitely help me to think about this. So going with the method I had before, my a in the formula would be an x, and my b in the formula would be a 3. When I'm choosing the formula, I'm going to choose the formula on the top because there was a plus sign in between these two. It usually helps me if I come over here and I write out, I know I have a 2 term times a 3 term. I know that my signs always go same, opposite, always positive. So I'll usually write those signs down first. That way I don't have to worry about them as I keep going. I know that the first term is just each of the cubed roots of these numbers, so x and 3. Then in the second one, the ends are the squareds, so x squared is x squared, and 3 squared is 9 on the other end. And then in the middle, I have the product of the two numbers, which were x and 3. So I have 3x, or x3, and I would just normally write it in that order. So that's where those things come from. Okay, let's look at the next one. The next one, I have x cubed minus 8. Again, this minus is going to be part of the formula. So when I come over here to do my final factoring, I know my first sign is the same as the problem, so it's a minus. The second sign is the opposite of the problem, so it would be a plus. And the third sign is always positive, so I can jump right ahead and write those signs down. Then I have to look at what A and B are. In this case, my A would be x again, and x would be the first thing I put in my factoring. And 8 is 2 cubed, so that means my B is 2, and 2 would be the second thing in my first factor. Then I need to write the 3-term factor. My 3-term factor would start with a squared, which in this case is x squared, and on the end it would be 2 squared, which is 4. So I did the 2 squared, and that's how I got the 4. In the middle, I have the product of the a and the b, or 2x. And this is the answer of the factors. Okay. In C, I have a little more complicated one, because for this problem, my first term has both a number and a letter. If I have both a number and a letter together, I have to be sure they're both cubes. So 27 is 3 cubed, and x is cubed is x, so in this problem, my A is 3x. Then I have the 8. Well, is 8 a perfect cubed? Yes, 8 is 2 cubed, so my B is equal to 2. Remember, in the original problem, I had a minus, so that means I need to use the formula for the difference of cubes. So coming over here into my factors, the first sign is the same as the original problem, then the opposite of the original problem, and always positive because it's squared. Then I'm going to write down each of my terms in my first factor. My first term is going to be a 3x, because that's the cubed root of 27x cubed. My second term is a 2, because that was the cubed root of 8. When I come over here into the second factor, my quadratic factor, this first thing here is a 3x squared. I'm squaring both the 3 and the x, which is how I got 9x squared that's written down on your paper. The last term is 2 squared, which is where the 4 came from. And the middle term is the product of those two. So I have the product of 3x.
Miss Molino, please call 6518. Miss Molino, 6518. Thank you.
And 2. So 3x times 2 is where my middle term came from here, of 6x. Pause the video while you try the 4 problems at the bottom of the page. You can check your answers for 1 through 4 here. Remember, in order for these problems to work, the numbers have to be cubes, nice cubes like 1, 8, 27, 64, nice cube numbers. If you turn this worksheet over, the other side says factor, 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 and it has a whole bunch of mixed types of factoring together. So if we look at this side, we can see number 1, number 2, number 3, none of those were cube problems. They were all squared problems. The first one I have that's a cube is number 4. So let's look at that one. In number 4, I have v cubed plus 1. In order to check that this is a difference or sum of cubes, I have to check, are they both cubes? Well, v cubed is a cube and 1 is 1 times 1 times 1, so I can do this following my pattern for the sum of cubes. Pause the video while you give this a try, and then check your answer. So I followed the pattern using the sign, same opposite, always positive. When I did 1 squared, it was already 1, and then I rewrote my answer down here in the box, but just simplifying the expression above. You can pause the video if you want to complete the rest of the factoring worksheet and then check your answers, or you could just check your answers online using the PDF. Here's 1 through 6. You can pause the video if you want to check these. Realize that for both number 5 and number 6, you could write the answer 2 different ways. You could either write it as the 2 factors multiplied together, or since they were the same factor, you could write the factor 1 time with a squared with it instead. Doesn't matter to me which way you write it, but you should recognize that they're both the same answer. So here's 7, 8, 9, and 10. On number 7, you take the 2 out as the GCF. Then what you have left inside is 64 minus x squared. That's a difference of squares, so it can factor further into the 8 plus x and the 8 minus x. So I have to factor completely. I always have to check to be sure. When I think I'm done, can I factor what I have left some more? On number 8, I take out a 3 as the GCF, and then I have q squared plus q plus 4. Well, I would think that probably q squared plus q plus 4 might factor some more. So I tried to do the product sums over there on the right, and I couldn't get 2 things that multiplied to 4q squared and added to 1q. So I know that that one was done. Number 9, after I got the GCF out, I could factor some more, which I did over here. Number 10, I factored the GCF out, and what I had left was r cubed minus 3. Well, my method for factoring that should be a difference of cubes, but 3 is not a perfect cube, so I can't factor that anymore. Pause the video if you still need to look at this, because I'm going to scroll down some and do the last couple. Number 11 looks like a doozy. I've got some big exponents here. It has 2 terms. My method for solving something with 2 terms is first look for a GCF, which there isn't one. Then I'm going to hope it's either a difference of squares or a sum or difference of cubes. If you recognize that this is a difference of squares, then you can jump right into the factors. If you wanted to factor that using boxes instead, we would be looking for what 2 things multiply to negative 225 n to the 4th p to the 6th, and they add to what's in the middle. Well, there's nothing in the middle, so they have to add to 0. We know that when we have to add to 0, that means the 2 things we're multiplying together have to be the same, where one is a plus and the other is a minus. So looking at the variables, normally I could just, change my x squared to an x, but I've got a lot of things here. N to the 4th is going to come from doing n squared times n squared. P to the 6th is going to come from doing p cubed times p cubed, because these have to be the same. So I essentially just took half of the exponents, because when I multiply 2 things, I add their exponents back. Then what 2 numbers multiply to 225 that add to 0? Well, this better also be a perfect square, and it is. 225 is 15 times 15. So if I want to put this in the boxes, in my boxes, I would have 225 n to the 4th, and I would have my minus p to the 6th from the original problem. Then when I split my middle 2 terms, it's 15 n squared p cubed and minus 15 n squared p cubed. The GCF of the top row is 15 n squared. So then up here I would also have a 15 n squared. And on the end here I would have a minus p cubed. Down here on the bottom, I would have a plus p cubed, and when I do my check, plus p cubed times minus p cubed is minus p to the 6th, so that's good. Again, I probably would have looked at this problem and said from the beginning, those are two perfect squared things. 225 is 15 times 15. N to the 4th is n squared times n squared. We've got the minus, so I need one to be positive, one to be negative. And p to the 6th is p cubed times p cubed. This is done because my only hope would be that I could then factor again using a sum or difference of squares or cubes again. And I can't since the n's are squared and the p's are cubed. So I'm all done. So on number 12, I went ahead and multiplied using the boxes, or you could have noticed the pattern of square double square, which makes this a perfect square. Either way, you should wind up with 4c plus 5d as a factor twice, which again, you can either list it out twice, or you can list it out once and put that squared up in the exponent. Pause the video if you need to look some more, because I'm going to scroll down. And here's the last two. 13 has a GCF that comes out, and then we can't factor it anymore. We cannot factor a sum of squares because we can't do anything to make the two terms drop out in the middle. Number 14, I want to start by factoring it like a difference of squares, like a squared minus b squared, except since we have 6th powers, these are going to be cubes in the exponent. And then I could factor the a cubed plus b cubed, that's what I did in blue, using my formula from the front of the sheet. And I want to factor a cubed minus b cubed, that's what I did in green, using the formula from the front of the sheet. And I have 4 big factors there.